Good morning, everyone. So in today's session, we are going to discuss organization of records in files. So far, we have studied how records are represented individually. And also, we have seen one mechanism known as slotted page mechanism that is used to store the records in a block. And that too, the records were variable length records. Now, in fact, if we talk about an instance of a relation, it is set of records, right? So we need to store the set of records from the relation into a file. So we are going to discuss how to organize the records in files. No doubt, files are comprising of various blocks, right? So how actually to organize the records in a file? So we are having several ways to organize the records in files. So the very first is the heap organization. So in this organization of records, a record can be placed anywhere in the file where there is a space, right? Second kind of organization is sequential organization. So here we store records in sequential order based on the value of a search key of each record. We are going to focus upon this in a while. Sequential organization of records, right? We are not going to talk about this heap organization right now, but we'll be talking about this sequential file organization, right? Next is hashing. A hash function actually is computing some key values, or rather some addresses based on the key values. So a hash function is computed on some attributes. Those are the key values, right? For each record, and they produce some address. So whatever is the result that has been computed by a hash function, that result specifies in which block of the file the record should be placed, right? As I mentioned earlier, one file comprises of several blocks. So whenever we would like to store a record in a file, that record definitely goes to a particular block. So we need to identify, or file organization methods need to identify in which block that particular record will go, right? So in hashing, there is a mathematical function known as hash function, and that hash function takes the input as one or more attributes from the relation, and for every record based on that attribute value, some address is being computed. So whatever is the result that is produced by our hashing function, this result specifies the block where we need to put that particular record, right? So we are going to discuss hashing methods also in detail, right? The next file organization method is the multi-table clustering file organization. Multi-table clustering file organization. So generally, the records of each relation may be stored in separate files. But many times it is the requirement that the records from various relations need to be stored in a separate file. or in same file, meaning if I'm having instructor table and if I'm having department table, then the records from both these relations I want to store in the same file. And the motivation for this kind of mechanism for storing the records is we would like to minimize the IO operations. Those are required to fetch the records from block or to store the records on block, right? So we are going to discuss this multi-table clustering file organization as well. So today we are going to discuss sequential file organization and multi-table clustering file organization. Later on, we are going to focus upon these hashing techniques with respect to both file organization as well as indexing. So afterwards, we are going to look at these hashing file organization methods and hashing indexing methods together, right? So today we'll be focusing upon sequential file organization methods and multi-table clustering file organization methods, right? Now, let us begin with the sequential file organization. Typically, the sequential file organization is suitable for applications that require sequential processing of the entire file. So what we mean by sequential processing of the file? Say for example, we are having this relation, right? So which is this relation? This relation is the instructor relation. Okay, and suppose I want to process those records one after another in the same sequence, right? So this instructor relation is right now organized based on the search key value, that is ID. So the records are organized with respect to this instructor ID, right? And whenever in my applications I require frequently such kind of sequential processing of the entire file, then the sequential file organization will be suitable, right? So here, as I stated, the records in the file are ordered by a search key. So what we mean by a search key? Search key is a single attribute or even it is the set of attributes. In this particular example, we are having a search key that is ID, a single attribute. Right? So a search key is any attribute or set of attributes in a relation. Right? It need not be a primary key or even a super key. Need not be. The search key may be any attribute or set of attributes in a relation. I repeat once again, it need not be a primary key or a super key. Any attribute can serve as the search key as per the requirement. Right? Now, to permit fast retrieval of records in search key order, we chain the records together. To permit fast retrieval of records in a search key order, what we do is we chain these records together in a search key order, right? And that is why how we are going to chain those records. We are having the pointer associated with every record. So the pointer in each record points to the next record in search key order. Right? Now, minimize the number of block accesses in sequential processing. Records are stored physically also in the search key order. or as close to the search key order, because we would like to minimize the number of block accesses in sequential processing. So what we mean by that? See here, suppose my search key order is based on this ID of the instructor. Right? Now, we have shown here the records of this instructor relation ordered in this search key order, that is ID. Okay? And every record is having associated with a pointer that is pointing to the next record in the order of search key. Right? So, in this particular example, our physical order of the records is same as the logical order of the records. What does this mean? See, physically on the disk also we are storing, or in the file also we are storing these records in the same order. So physical order is also maintained in this particular example. Right? But this is not always the case. Sometimes it may happen that, say for example, I am having one more record here, say 33912. ID is 33192. So ideally, this record should be placed after this 33456 to maintain the sequential order of IDs, right? But physically, now my file is stored already. My records in file are stored already, right? So if I'm inserting this new record, there is no space actually to store this record in physical sequence. So what I can do is I can place this record somewhere else in some other block, right? And I can maintain the pointer of this 33456 such that this pointer will point to the record that is stored in other block. And once again, the pointer of this record will point to this 45565 so that the sequential order of search key is maintained. Right? So records are stored physically in search key order or as close to the search key order as possible. And the reason is we want to minimize the number of block accesses in sequential processing. So what we mean by these block accesses? See, whenever I want to read a particular record, then the entire block where that record is placed, that block is being read. Okay? Now, if I am not having the records sequentially in the physical order, meaning even though, like this case, even though after 33456, I need to read this 33912, but this record is placed in some other block, the physical order is not maintained, although the logical order is maintained by making use of the pointers, but physical order is not maintained. So in such scenarios, if I'm processing the record sequentially, what happens is I need to read the other block as well, where this particular record is stored. So the number of block accesses are increased, right? But in sequential file organization, we are aimed to minimize the number of block accesses. And that is why we try to store the records physically in search key order, or if it is not possible, we try to put those records very close to one another. so that those records can be accommodated in a single block as far as possible, right? So that only that block can be read. Are you getting me?
Yes, ma'am.
Yes, ma'am.
Fine. So let's proceed now with one more important concept related to the sequential file organization. As I mentioned, the pointer in each record points to the next record in search key order, right? But sometimes it may happen whenever we are inserting some new records or whenever we are deleting the record from the file, it may happen that we are not able to maintain the physical sequential order of the records, right? So sometimes it happens. So if it happens, what to do, we are going to discuss in a while, right? So before that, we'll see how this insertion and deletion operations are performed with respect to the sequential file organization. So see here, we are having a sequential file organization, and if we want to delete a particular record, right? So after deleting a particular record, we need to update the pointer chains. Meaning, if I'm deleting this particular record, then after this, earlier the pointer was pointing to this record that is now being deleted. So this pointer needs to be updated so that this pointer can point to the next record, right? So such deletions need to be handled properly by updating the respective pointers of the records. Also, as we have seen earlier, if we are having the deleted records, we may use the free lists for the number of records those are deleted. So whichever are the records those are deleted, we may maintain a free list also for deleted records. Okay. Now, as far as this insertion process is considered, what we are going to do? We need to maintain the order, the search key order. Here our search key order is ID. So whenever I want to insert a new record, what I'll do is I'll locate the position where the record needs to be inserted. Right? So if it happens that there is a free space available at the located position, then it is possible for us to insert the record at that free space. Okay, no issues. And we can maintain the physical order of the records. But if no free space available to insert the record in the physical order, what we need to do is we need to insert the record in an overflow block. So see here, we wanted to insert this record with ID 32222. So the location where we need to insert this record is after this record 22222 and before the record 32343. So physical order to place this record is this. Sorry. Physical record to put this particular physical order or physical location where we need to put this record is this, right, in between these two records. But now if we look at, we are not having any free space available here. So what needs to be done is the new record that we want to insert is being inserted into the overflow block. So this is our overflow block. And as I mentioned earlier, the pointers are being updated. So the pointer of 22222 is now pointing to the record in the overflow block. Right? So this will take us, after reading this record now, the system will take us to the overflow block. We will read this record, and once again, pointer of this newly inserted record is pointing to the next record in order. So it is pointing to this 32343. So this is how actually the logical order of the records is maintained, even though it is not possible for us to maintain the physical order, because there is no space available to insert the record. Right? But even though we are inserting the record in the free space available, or if we are inserting the record in the overflow block, in both the cases, pointer chain must be updated. Please remember. So this pointer chain is actually giving us the order of the records. Right? Now, if relatively few records need to be stored in overflow blocks, this approach works well. I repeat, if relatively few records need to be stored in overflow blocks, this approach works well. But if I am having frequent insertions or frequent deletions in the table or in the relation, then it would become very difficult to maintain the physical order of the records. And if the physical order of the records is not maintained, then obviously the number of block reads to read or write the records are more. Right? So eventually, if I am having many number of insertions or deletions, then the correspondence between search key order and the physical order may totally be lost. Right? And in such cases, such kind of sequential processing will become less efficient. Right? So, in these scenarios, many times we need to reorganize the file, right, in periodic manner. So, after some period, we need to reorganize the file to restore the sequential order of the records in physical manner. The frequency with which we are reorganizing the data or we are reorganizing the records depends on the frequency in which we are inserting or deleting the records. So if there are many number of insertions or deletions in the relation, then the frequency of reorganization is more. But let me tell you, if we are reorganizing the file, it is once again the time consuming process. A reorganization of file is costly, and that must be done during the times when the system load is low. So during normal process, when the system is being used heavily, it is not possible to reorganize such kinds of sequential files. So whenever there is low load with respect to our application or the database system, database administrator will decide or will schedule when to reorganize the files, right? But the important point that needs to be noted is whenever we are having frequent insertions and deletions, we do not go with this sequential file organization because the overhead associated with reorganization of file is much more. Right? So typically, whenever we are having the applications where the data is being stored once, okay, and the application needs to read the records or to find the reports, in such situations where the records need not be inserted frequently or the records need not be deleted frequently, we may go with this sequential file organization. Otherwise, it becomes inefficient. Right? So I hope you must have understood what we mean by the sequential file organization. What are the advantages of this sequential file organization and what are the disadvantages? When we should think of this file organization and when we should not go for such kind of file organization. If you have any kind of doubt, please let me know. Let's proceed to multi-table clustering file organization. So many relational database systems actually store each relation in separate file. So as far as simple file structures are considered, the simple file structures are stored like each relation is stored in a separate file, so that they can take full advantage of the file system that is offered by our operating system. Usually, tuples of a relation can be represented as fixed length records, right? And in such situations where we are having fixed length records, the relations can be mapped to a simple file structure. And if the records are mapped to a simple file structure, it is better to store each relation in a separate file. Right? So this simple implementation of a relational database system is actually well suited to low cost database implementations. For example, if we are having some embedded systems or portable devices. So in case of embedded systems or portable devices, obviously the databases, those are being stored in such portable systems or the embedded systems are very small. Right? So in such kinds of situations, low cost database implementation, such kind of use of separate file to store a single relation may be well suited. Right? Because such kind of implementation reduces the amount of code that is required to implement the system. Because in case of embedded systems or in case of portable devices, as you know, the storage requirements are also limited, right? And that is why we need to have minimum overhead associated with the code as well. So if we go with such kind of system, low cost database systems with one relation, one file mechanism, it reduces the amount of code as well that is required to implement the entire system. But such kind of approaches become less satisfactory if the size of the database increases. Right? So if I am having very huge database systems, then to store such kinds of large scale database systems and even to manipulate those relations stored in the large database systems are having some extra demands. And these large scale database systems do not rely on the underlying operating systems for managing the files. So instead, in such large-scale database management systems, one large operating system file is allocated to the database system, and the database system stores all the relations in this one file. And this large database file, wherein all the relations are stored in a single file, is managed by the database system itself. I repeat the concept so that you can understand it better. So what I mentioned, if I am having small databases, then to store small databases, obviously the database manipulation requirements are also limited, right? And that is why for such kinds of low cost database implementations, having the small databases, we may rely on the file system that is provided by the operating system. So operating system files can be used to store one relation per file. And it is easy to manipulate on those relations, even though these are stored into separate files, because the database size itself is very small, right? However, whenever we switch to the large databases, say for example, we are having our university schema. So in our university schema, we are having many relations. Those we need to store. And also these relations are related with one another in various different aspects, right? And we need to manipulate those relations frequently. So in such situations, what we can do, or what large database systems can do, they allocate one single file which is very large, right? So from operating system. So underlying, whatever is the underlying operating system, one large file is being allocated for storing entire database. And whatever are the relations in my database, all those relations are stored in the same file. So all relations in same file are being stored. Right? Now, in such situation, the database management system itself is taking care of handling this file, and all those relations, those are stored in a single file. Right? Now, let us take one example so that we can understand this multi-table clustering file organization in a systematic way, right? So, as I stated, we are having several relations in a database, and the multi-table clustering file organization stores more than one relations in one file. So let us assume that we are having this department relation and this instructor relation. So we are having two instances of department relation and instructor relation. Right? Now, sometimes it may happen that this individual relation, say for example, this department relation is stored in one block of file, And this instructor relation is also stored in another block of file. So all instructor records in one block, all department records in one block, all student records in one block, and so on. Right? So many times it happens that even if multiple relations are stored in a single file, by default, most databases store the records of individual relations in a separate block to simplify the database management. Right? However, in some cases, it can be useful to store records of more than one relations in a single block. Are you getting me? See, we are having various terms. We are having disks, we are having files, and we are having blocks. Are you able to understand all those terminologies? Yes? Are you able to understand those terminologies?
Yes, ma'am.
So, see, in large databases from operating system, we take one single file. Right? So this one single file is comprising of many blocks. Right? So if I am having say 50 relations, 50 different relations in my database system, then all those 50 relations are being stored in a single file. Many times a strategy is adopted that most databases store records of individual relations in a single block. So this actually simplifies the data management task. What does this mean? This means that no doubt a single file is being used, but in this single file I am having different blocks. So one block is being used to store department relation. Few blocks are being used to store instructor relation, and so on. So in one single block, only one kind of records are being stored in many cases, right? So that we can simplify managing the data. However, in some cases, it can be useful to store the records of more than one relations in a single block. So instead of having different block for department relation and different block for instructor relation, sometimes it is useful to store the records of both these relations in a single block. Right? So, see here, this is the multi-table clustering organization of department and instructor. See here, what has been done? If you look at this tuple is from department table or department relation. These tuples are from instructor relation. Once again, this tuple is from department, right? And this tuple is from instructor relation. Right? So multi-table clustering organization actually allows us to store the tuples belonging to different relations in a single block. So what is the motivation? Why we should store the records from different relations in a single block? What is the motivation behind? See, if I'm having frequent queries in my database system. So if I'm having frequent queries, those demand for joins of the relations. So obviously, whenever I'm performing such kinds of queries, wherein I'm having joins of the relations, then obviously if the data or if the related data from both the relations, if the data is kept together, then obviously the time required to get that data is minimum. The number of I/O operations those are required to read or fetch that data is minimum, because the related records are stored in single block even though they belong to different relations, right? So such kind of a file organization scheme is good for the queries those involve the natural joins of various relations. So if I'm having SQL statement like select department name, building budget, ID name, salary from department, natural join instructor. Here what I need to do is I need to find the natural join of department and instructor. If these two relations are stored in different blocks, then what will happen? I need to fetch the data from the block where department relation is stored. I need to fetch another block where the instructor records are stored. So I need to read from two or more different blocks. And obviously, if I'm having many number of I/O operations or read and write operations, then these are most expensive operations, right? And if we are having frequent queries in our database, those require to have the joins of different relations. Then how the data can be organized? We may come up with, or we may go for multi-table clustering file organization, wherein the related relations are stored in a single block, so that only one block read can get the data from both the relations, and it is possible for us to execute such kinds of natural joins efficiently, right? But such kind of organization may be bad for the queries those involve only fetching the data from department table, right? So once again, there are pros and cons for this file organization mechanism. So as I stated, when we are having frequent queries of joins, then we should go for this multi-table clustering file organization, so that the related records from different tables or different relations can be stored in single blocks, right? But if we need to have the data, or we need to retrieve the data from individual tables, and such kinds of queries are frequent, then this may not be good technique to store the data, right? Also, please note here, in this kind of file organization, we are having variable size records, right? Because we are storing the record from department table, we are storing the record from instructor table. So obviously the size of this record and size of this record is different. Okay, now if we are having a query like we would like to extract the departments. So we are having the query like select star from department, and we are using multi-table clustering file organization, wherein the data from department table and the data from instructor table are stored in same block. Right? As I stated, if I am having such kind of a query, we may require more block accesses. And the reason is, see here, one department, then all instructors, then next department, then all instructors, and so on. So if we are organizing data in such a way, then obviously more than one blocks are being utilized to store the data from department and instructor table, or records from department and instructor relation, right? So it may require to have more block accesses if we want to execute such a query, select star from department, right? Also, if we want to use multi-table clustering file organization, and if we are interested in using such kinds of queries, then obviously we need to add some additional structure. And that additional structure is a pointer that is actually pointing to the records of the same relation. So this record is from department relation. The next record from department relation is here. So we need to maintain a chain of pointers so that we can locate the records from department relation, and we can execute such kind of a query, select star from department, right? So I hope you must have understood this multi-table clustering file organization as well. So we have seen why or what is the motivation for this multi-table clustering file organization. We have seen how actually records are organized in this mechanism, how records from two different relations are being organized, when to use such kind of file organization method, and when there is a limitation of such kind of file organization method, right? But definitely, whenever we are having frequent queries like joins, we should go with such kind of file organization, right? So that we can efficiently implement the joins of various relations. I hope you must have understood this concept. If you have any doubts, please let me know. Fine. So let's conclude today's session. In the next session, we are going to discuss about the data dictionary and buffer management in database systems, right? And further, we'll go for indexing. So let's conclude today's session. Thank you.